Welcome to the deep dive. We're here to, well, shake up some things you thought were settled facts, see what falls out. And today, we're tackling a big one, a really fundamental piece of environmental knowledge, where the air we breathe actually comes from. For years, maybe decades, conservation talk, especially globally, it almost always circled back to rainforests. We all grew up hearing it, didn't we? The Amazon is the lungs of the planet. It paints such a picture, right? These huge green forests just pumping out oxygen. But what if that picture, that powerful metaphor, what if it's actually, well, misleading? What if the place we think keeps us alive is really more of a supporting act?
It is misleading, yeah. The sources we've looked at today, they don't just tweak the picture, they pretty much repaint it entirely. Now, don't get me wrong, forests on land, absolutely vital, we need to protect them. But the really startling truth is that most of the oxygen you're breathing right now, it didn't come from a tree, it actually came from the ocean.
Okay, wow, that's a huge shift in thinking. Lungs of the planet. We automatically see green. So today, we're asking you to picture blue instead. Our mission. Let's unpack who, or rather what, is doing this massive job, these unseen oxygen factories. Why the ocean? Why is it the real engine room for Earth's air?
Right. Let's start with the headline fact, the one that honestly should make you stop and think. The scientific consensus, looking across multiple studies, is that somewhere between 50 and 70%, maybe even more, of all the oxygen on Earth, it's made by microscopic life floating in the sea.
50 to 70%. So
Yeah.
take a deep breath right now. At least 1 out of every 2 oxygen molecules you just took in is made by something you can't even see.
Exactly. An invisible majority basically running the planet's life support system.
And these producers, what are they called?
They're called phytoplankton. Phytoplankton. Think of them as tiny single-celled plants, essentially. They just drift near the ocean surface. And even though they're incredibly small individually, their combined effect is, well, it defines our atmosphere.
Yeah.
It's a total biological paradox.
Tiny but mighty on a planetary scale. So how do they do it? What's the actual mechanism?
It's photosynthesis, just like land plants. They take in carbon dioxide that's dissolved in the seawater, use sunlight for energy, and poof, out comes oxygen as a byproduct.
Okay, photosynthesis. But the ocean is huge. What makes it happen? What conditions do they need?
Well, 2 key things need to come together. First, like you'd expect, sunlight. It needs to hit the surface waters where the plankton live.
Right, the energy source.
And the second part, this is where it gets really interesting and connects different parts of the marine ecosystem in a perhaps surprising way. It involves the biggest animals in the sea, whales.
Whales. How do whales fit into microscopic oxygen production?
Okay, so the phytoplankton, they need nutrients to grow and photosynthesize efficiently. Things like iron, nitrogen, essential stuff. But these nutrients, they tend to sink down deep into the ocean, far from the sunlight.
So you've got the sunlight at the top, the food at the bottom. How does that work? How do the phytoplankton get fed consistently enough to make that much oxygen?
This is where researchers talk about something called the whale pump. It's a fascinating concept. When whales dive deep to feed, sometimes really deep, they're consuming creatures that have absorbed those nutrients locked away down there.
Okay.
Then the whales come back to the surface to breathe. And what do they do when they're up there? They excrete waste. And that waste is packed with those exact nutrients. Iron, nitrogen delivered right into the sunny surface layer, the euphotic zone where the phytoplankton are waiting.
Wow. So the whales are like giant swimming fertilizer distributors, bringing the deep sea nutrients up to the surface garden.
That's a great way to put it. It's literally a biological pump.
Yeah.
Think about tending a garden on land. You
Yeah.
add fertilizer.
Right.
Whales are doing that for the ocean surface, naturally. They help ensure these incredibly numerous and efficient phytoplankton get the fuel they need to produce, well, more than half the air we breathe. It's this incredible link between the largest animals and the absolute smallest, all working together, ultimately, for our benefit.
That adds a whole new layer. It's not just passive little dots floating around. It's this active, interconnected system. Which brings us back to the big question, if the ocean, this blue system, is doing 50, maybe 70% of the work, why? Why did we all grow up thinking it was just the trees? Why isn't this common knowledge?
Yeah, that's a really important point the sources touch on. It seems to come down to human perception, how we process information. One source called it a glitchy reflection. It's just simpler for us to grasp and connect with things we can actually see and touch.
Tangibility makes sense.
Exactly. A forest, it's right there. It's big, it's green. You can see if it's healthy. You can see if it's being cut down. It gives us a very direct visual feedback loop.
Easy to point to, easy to rally around.
Precisely. How do you rally people around? protecting something microscopic out in the middle of the ocean. We're just sort of wired to react more strongly to visible things, visible threats, visible solutions.
So our attention, our conservation efforts, even our metaphors, they naturally lean towards the things that give us that immediate, maybe emotional connection, like the big, iconic forests. But that focus, that visual bias, means we've kind of overlooked the main engine room. If we can't easily see the plankton, it's harder to grasp their critical role, isn't it?
It is. And it means we don't necessarily give their protection the urgency or the resources it deserves.
We don't instinctively connect ocean health with, the air we're breathing moment to moment.
That's the danger of the glitch.
Mhm.
We often treat protecting the ocean as, well, maybe an issue about saving whales or coral or managing fishing stocks. All important, absolutely. But we don't always see it as fundamental atmospheric survival. Realizing this hidden truth, that's the aha moment. Protecting the ocean, especially the open ocean's health, that's about protecting our ability to breathe.
Okay, that definitely shifts the perspective from just wonder towards, frankly, urgency. Because if the ocean's health is our air supply's health, then we absolutely need to talk about the threats. What's putting these crucial, invisible oxygen producers at risk right now? Because their stability is, well, it's critical for everyone.
Yes, we have to pivot from the marvel of the blue lungs to the very real danger they face, a sort of planetary respiratory risk, you could say. And the sources highlight a kind of triple threat, really, endangering this whole system. And it's all linked back to human activities.
Okay, let's break those down. What specifically is harming the phytoplankton?
First, there's general pollution, stuff like plastics, chemical runoff from agriculture and industry. It degrades water quality. Phytoplankton are sensitive, they need specific conditions to thrive, and pollution just disrupts that delicate balance.
Right, the direct contamination. What else?
Second, and this is a really big systemic one, ocean acidification.
Acidification. We hear that term, but can you unpack what it actually means for the listener? How does it work?
Sure. So we release huge amounts of carbon dioxide, CO2, into the air, right? The ocean acts like a giant sponge, soaking up about a quarter of all that CO2 we emit. But when CO2 dissolves in seawater, it undergoes a chemical reaction and forms carbonic acid. This lowers the pH of the water, making it more acidic.
And it's happening fast.
Worryingly fast, yes. The ocean chemistry is changing at a rate unprecedented in perhaps millions of years.
And how does more acidic water hurt the phytoplankton?
Well, many types of phytoplankton, including some of the most productive ones for oxygen, build tiny shells or skeletons out of calcium carbonate. As the water becomes more acidic, it gets harder for them to form these structures. The building blocks essentially become less available, and the water itself can even become corrosive to existing shells.
So the very water they live in starts working against them, dissolving their structures.
In effect, yes. It undermines the foundation of their life cycle for many key species, potentially leading to big population declines in those groups that give us a lot of oxygen.
Okay, so pollution, acidification. What's the third threat?
Warming waters. Climate change is heating the ocean surface.
And how does warmer water cause problems? Seems like plants like warmth sometimes.
It's about how the ocean mixes, or rather, how it stops mixing. Normally, you have colder, nutrient-rich water deeper down. Temperature differences help drive currents that can bring some of that nutrient water up towards the surface. But as the surface layer gets significantly warmer, it becomes much lighter and more buoyant than the colder water below. It forms a stable layer, almost like a lid.
Ah, so it traps the nutrients down below?
Exactly. It prevents that natural upwelling, that mixing process. So the phytoplankton at the surface, already potentially stressed by pollution and acidification, also get starved of the nutrients they need. Even with the whale pump helping, this stratification makes it much harder.
Wow. So it's a triple whammy. Pollution and acidification are like direct attacks, and warming waters are cutting off their food supply from below. The implication seems incredibly serious. If phytoplankton numbers crash because of this combination, we're not just talking about a vague future climate issue. We're talking about potentially crippling the system that makes most of the oxygen we breathe, like, now.
That is the profound vulnerability. It's perhaps the biggest blind spot in how we often frame environmental action. We focus heavily on cutting CO2 emissions, which is absolutely essential. We have to do that. But we sometimes miss the immediate impact those emissions are already having on the very biological systems that help buffer the planet, like the ocean's oxygen production.
We're treating our primary oxygen source like a dump in a heat sink all at once.
That sums it up pretty well, unfortunately.
Okay, so let's bring this together. We started by questioning that old lungs of the planet idea about forests, and we found that actually it's the microscopic phytoplankton, helped out by whales cycling nutrients, that are responsible for what, more than half, maybe up to 70% of the air we breathe. It's a pretty staggering realization, isn't it? How much we depend on this invisible world.
It absolutely is. That's the core takeaway. So the next time you take a breath, maybe just pause for a second. Think about the ocean currents. Think about those giant whales diving deep. Think about this invisible life doing the quiet, constant work of making our world habitable. Maybe, silently thank the blue lungs.
The ocean isn't just holding water, it's holding our breath, our future. And that leads to the final thought we want to leave you with today. It's about action, about what comes next. If we truly accept this, that our air supply hinges on invisible marine life under threat, then what specific urgent steps beyond just general climate targets do we need to take right now to protect that vital ocean surface layer, to ensure the whale pump keeps working, to buffer against acidification? What does effective blue lung protection actually look like in practice? Because really, the next breath you take kind of depends on finding the right answers.